Now we are going to use support vector machine to classify iris dataset. The iris dataset, it contains information about three different types of flower: versicolor, setosa, virginica. Each one of these flower, they have a different petal length and petal width, different sepal length and sepal width. Now, this iris dataset is present inside a CSV file. So this CSV file contains sepal length, sepal width, petal width, and species. And there are three different types of species: setosa, and if you scroll down a little bit, you're going to see versicolor, and scrolling down some more, and we are going to see virginica. So it has three different types of species. So the first thing I do is I import my pandas as PD. Then I do my data collection. I load my CSV file. So this is my CSV file I just showed you. And I load it and I just print few records. And you can see it prints out few records right there. And these are 5 records. So this one tells you the sepal length is 5. Tells you sepal width is 3.6 and petal length is 1.4. Petal width is 0.2. And this particular data, or this particular flower is Setosa. Now I want to see the shape of my data. I want to know how many rows and columns I have. So in this case, I just print df.shape. That's going to tell me it's 100 total, 50 rows and 5 columns. So you can see that 1, 2, 3, 4, 5, 5 columns. And I want to see the values of my species. I want to see what are different type, different value counts of my species. So in this case, you can call this inbuilt method value counts. That's going to give you the individual values or individual counts for each one of those values inside the species column. Setosa, there are 50 records. For versicolor, there's a 50. Virginica has 50. Now I'm going to separate my features and target. So my X is going to be all the values except the species. I'm dropping the species, and my Y is going to be the species column. In other words, coming down over here, this is going to be my X right here. All this thing, all this data right here, that would be my X. And this will contain sepal length, sepal width, petal width. This is my X, and my Y would be this right here, this particular column. Okay, scrolling down. So now I'm going to encode my Y. Now, if you look at your values of Y, they're all text characters. And machine learning, they don't like text characters, they like numbers. So I'm going to convert them into numbers. So in this case, I'm calling my, importing my label encoder. I'm calling this inbuilt method fit transform. I'm passing my Y to that. And then I'm printing my encoding. So in this case, it's going to encode Setosa to 0, is going to encode versicolor to 1, and Virginica to 2. Let's take a look at some of the first 5 values of my Y encoded. So this is my new Y encoded. So let's run this, and that's going to print out the first 5 values are 000. So this is basically Setosa. If you recall, the first 5 were all Setosa. You see that Setosa, Setosa, Setosa. So it's all printing 000. First 5 is 000. Okay. After that, I import this train test split function, and this function I'm giving my X, and I'm passing my Y encoded, not my Y, but Y encoded. In this case, I'm specifying my test size should be 30%. And this actually produces X train, X test, Y train, and Y test. And after this, now we do feature scaling. So it's very important to do this for SVM. That's because your SVM is a distance based. In other words, if you remember, we were trying to find the maximal separating hyperplane in SVM. And because there's a concept of distance involved, you have to do scaling. So in this case, I'm using standard scaler. So I call my standard scaler right here, and I fit and transform. So the purpose of fit basically is to learn the mean value standard deviation from your training data. And after that, I do the same thing to my X-test data set, but in the X-test data set, you do not call fit. And that's because that would leak the test information into your training process. You do not want that to happen. So that's why you just call only transform method. And after this, now I import my support vector machine. In this case, I'm importing SVC, which is short for support vector classifier. Well, this is a classification problem, so that's why I'm importing SVC. So in this case, I'm training my model. I'm passing my X train scaled, the data I just scaled, which is this right here. You pass your training data, and you also pass your Y training. And in this case, after I run this, it gets trained. In this particular instance, it got trained very quick because it's not a big data set. And I also want to print my hyperparameter. So you can actually access the hyperparameter by using the inbuilt method get params. And that's going to print all your hyperparameter. So in this case, the important ones are kernel, C, gamma, degree, decision function, say. So by changing these values to different values, you can actually find the one that gives you better accuracy and use that one. So just to give you an idea, for example, decision function shape. So you can use OVR. OVR means one versus the rest, and or you can use OVO, which is one versus the one. So you can read the documentation, and that's going to give you a little bit more information about this. Now let's make prediction on some of the points on this model. So in this case, this is my data right here. I just copied and pasted over here. So this actually was Satosa. This is 5.1, 3.5, 1.4, 0.2. This I got it from here. So this value is this right here, the first one. This one is this one right here. And likewise, I copied and pasted the other value, and that was Virginica. So this is my data, and then I calling my scalar, transforming my data to scale version, and then after that I'm passing my scale data to the model. So I'm calling my inbuilt method predict, and then I'm finding my prediction over here. So it gives me a prediction. In this case, it makes a prediction that is 0 and it's 2. If you recall, your 0 was, let's see, let's go back on top and let's look at our coding right there. 0 was Satosa and 2 was Virginica. So it made a prediction that the first one is Satosa, which is true. And you see, this is actually Satosa. And the second one is Virginica. Great. So it's working fine. You can also decode the labels directly, by the way. So in this case, I'm just taking the predictions right here and giving it to your LE label encoder. There's an inbuilt method called inverse transformation. What it does, it's going to take your prediction and return the label for you. So that's what this one does. It prints out the labels. For 0, it is Satosa. For 2, it is Virginica. Now let's predict on the test data set. So in this case, I'm feeding my X test scaled version, and it makes a prediction right here. And let's check the prediction for the first 5. So I'm printing the first 5 test value, and I'm also checking the predicted value for the first 5. So let's run this cell first and come over here. Let's run this, and there you go. So this is my first record right here. This is my sepal length, sepal width, petal length, petal width. I think that's what it is. Let's go check. Yeah, sepal length, sepal width, petal length, petal width. All right. So this is my first data set, and sorry, my first data. And for the first data, it predicts label 1. And label 1, if you recall, that would be versicolor. Yes, label 1 was versicolor. Okay, the second one is this right here. This one is making a prediction that is label 0, which is Satosa, and this one is making a prediction that is 2, which is Virginica. And likewise with this, it's 1, and for this one, it's 1. Okay, so I'm just printing the first 5 over here. Now let's compare the predicted versus the actual value on the test data. So in this case, I'm just doing the first 30. So I'm seeing the first what the model predicted, and I'm also looking at the actual value. So in this case, you can see that predicted, and this is my predicted right here, and this is my actual, and that's pretty on the mark. You can see that most of the values are same, except I saw there was one value that was not the same. And let's see if I can find this over here. Nope, I do not see there. So yeah, it seems like it's doing pretty good job. Everything is exactly identical. All right. So let's check this accuracy score. So I'm calling this method accuracy score. I'm actually first I import this method, and then you just call this, and you pass your y test, and you also pass your prediction, and that's going to tell you what is the accuracy. Oh, look at that, it's 100%. All right, and now we can also plot a confusion matrix. So this allows you to see how many of them were misclassified or confused. So in this case, you want to look at the diagonals. You want your diagonal numbers to be high, and your off diagonal numbers should be as low as possible. Ideally, there should be 0. So diagonal number means that everything was classified correctly. That's what it means. So higher number means everything is working fine. Let's do a confusion. Let's plot this on a heat map. So I'm taking this confusion matrix, I'm plotting this on a heat map, and there you go. So let me just decrease the size of screen. Okay, so what this is telling me, this is actually a same thing. This confusion matrix is essentially the same thing over here, just like pictorial, more like graphical representation in the form of a heat map. So in this case, you can see that all the diagonals are basically colored. They're all high numbers and rest of the numbers are zero. So the way you read this is basically, let's look at this number. This is telling me that the actual class was 1 and the predicted is 1. There were 13 of them that was actual 1 and 13 of them were predicted 1. So this is good. This one is telling me that 0 were actually class 2 and they were predicted as 0. In other words, none of them were misclassified. All of them were classified correctly. So these were all classified correctly. That's a good thing. Now you can also check the number of support vectors if you want. So in this case, you can access those number of support vectors per class by this model.n underscore support underscore. So this is going to print out the number of support vector for each class. So for class 0, the number of support vector is 7. For class 1, the number of support vector is 19. And for class 2, the number of support vector is 17. So 0, 1, 2 refers to Setosa, versicolor, and Virginica. Okay, and what if I want to see the support vectors? Well, that gives you the ability to. It prints out the support vectors too. So in this case, I'm just printing the indices, the index of that. So in this case, it prints out the indexes of my support vector. So this, by the way, is from the training data. So the 17th index, 18th index, 26th index, this is the support vector. Well, if you want to actually see the support vector, you can do that too. So just uncomment this line out and uncomment this line out too. And that's going to print out your support vector, which will be a scaled version. So if I run this, and that gives you that gives you all these support vectors. What if you want the actual original vectors? You want to see the actual original, not the scaled version. You can do that too. So let me comment these two lines out now and come over here and let's run this. And there you go. So this is the actual support vector, which is the unscaled version. All right, students, I hope this session helped. Thank you.